in last lecture we have seen the ideal current voltage characteristic of PN junction. Now we will see the next point, that is generation recombination process. So in ideal current voltage characteristic of PN junction we have seen the special case, that is Shockley equation. This Shockley equation gives the adequate predictions of the current voltage characteristic of the germanium PN junction at low current densities. For silicon and gallium arsenide PN junctions, the ideal equation can give only qualitative agreement, and the departure from the ideal are mainly due to some reasons. So we will see the departure from ideal current voltage characteristics in case of germanium as well as gallium arsenide PN junction. So the first reason is the surface effect. Surface effect. The next reason for this departure of current voltage characteristics are the generation and recombination carriers in the depletion region. In the depletion region, the third reason is the tunneling effect. The tunneling of carriers between states in the band gap. States in the band gap. The next reason is the high injection condition. The high injection condition that may occur even at relatively small forward bias. And the fifth reason is the series resistance effect. The series resistance effect. So, in addition, under sufficiently larger field in the reverse direction, the junction will break down as a result of avalanche multiplication. The surface effect of PN junction are due to primarily the ionic charges on or outside the semiconductor surface that induce image charges in the semiconductor and thereby causes the formation of surface channels or surface depletion layer region. Once the channel is formed, it modifies the junction depletion region and gives rise to surface leakage current. For silicon planar PN junction, the surface leakage current is generally much smaller than that of generation current in the depletion region. So, consider first the generation current under reverse bias. Because of reduction in carrier concentration under reverse bias, that is the product Pn is less than Ni square in reverse bias condition, the dominant recombination generation process are those of emission. The rate of generation of electron-hole pair can be obtained from the equation, that is U is equal to sigma p into sigma n into VTH into P n minus Ni square into Nt upon sigma n into bracket n plus Ni exponential of Et minus Ei upon Kt plus sigma p into P plus Ni exponential of Et minus Ei upon Kt. So this is equation number 1, where sigma p is the hole capture cross section and sigma n is the electron capture cross section. And sigma n is electron capture cross section. In this, the VTH is the carrier thermal velocity. VTH is the carrier thermal velocity. And The value of VTH is root 3 kT by m star. This VTH is equal to root 3 kT by m star, where m star is the effective mass of the charge carriers. Here Nt is the trap density. Nt is the trap density. And Et is the trap energy level. Trap energy level. Then EI is the intrinsic Fermi level and Ni is the intrinsic carrier density. Intrinsic energy level and Ni is the intrinsic carrier density. By applying the condition that P is less than Ni and N is less than Ni, one may write the equation number 1 as U is equal to here minus into the bracket sigma p into sigma n into VTH into NT upon sigma n exponential of ET minus EI upon KT plus sigma p into exponential of EI minus ET upon KT bracket complete into Ni. So this is next equation number 2. Again this also can be written as minus Ni upon 2E, where 2E is the effective lifetime. 2E is the effective lifetime. And the value of this 2E is nothing but the reciprocal of the expression in this bracket. The current due to generation in the depletion region is thus given by J generation, which is equal to integration over integration from 0 to W Q mod of U into dx, which is nearly equal to Q into mod U into W. Or which may be written as J generation, which is equal to Q into Ni into W upon tau E. So this is equation number 3. So this equation number 3 gives the current due to generation in depletion region, where W is the depletion region width. If the effective lifetime is slowly varying function of temperature, the generation current will then have same temperature dependence as Ni. At a given temperature, Jn is proportional to the depletion layer width, which in turn depends on the applied reverse bias. It is thus expected that the generation current, that is J generation, which is nearly equal to VBI plus V raised to 1/2. This is equation number 4, and this equation is valid for abrupt junction. This is for abrupt junction, and J generation, which is nearly equal to VBI plus V raised to 1/3. This is equation number 5, and this is valid for the linearly graded junction. Linearly graded junction. The total reverse current can be approximately given by the sum of diffusion component and sum of diffusion component in neutral region and the generation current in the depletion region. So the total reverse current can be given as JR, which is equal to Q into under root dP upon tau P into Ni square upon Nd plus Q into Ni into W upon tau E. So this is next equation number 6. For semiconductors with large values of Ni, such as germanium, the diffusion component will dominate at room temperature and the reverse current will follow the Shockley equation. But if Ni is small, such as for semiconductor like silicon, the generation current may dominate. A typical result for silicon is shown in this figure. So this figure shows the ideal reverse current, actual reverse current, ideal forward current, and this is the ideal actual forward current. So थांबवताय का जरा. At sufficiently high temperatures, the diffusion current will dominate. At forward bias, where the major recombination generation process in the depletion region are the capture processes, we have a recombination current in addition to the diffusion current. So now we have the equation for number of charge carriers, that is N is nearly equal to 1 upon root 2 ND into NC bracket raised to half exponential of minus ED upon twice KT. This is next equation number 7, and by substituting this equation in equation number 1, we get the equation number 1 as U is equal to sigma P into sigma N into VTH into NT into Ni square into bracket e raised to QV by KT minus 1. This is next equation number 8. Under the assumption that EI is equal to ET, and sigma N equal to sigma P equal to sigma, this equation 8 reduces to U is equal to sigma into VTH into NT into Ni square into bracket e raised to QV by KT minus 1 upon N plus P plus Ni square. So this is next equation number 9. or this equation again may be written as U is equal to sigma into VTH into NT into Ni square into e raised to QV by KT minus 1 upon Ni into bracket exponential of Q into psi minus phi n upon KT plus exponential of Q into phi p minus psi upon KT plus 2. So this is equation number 9a. The maximum value of U exists in the depletion region where psi is the halfway between phi p and phi n. So this psi is given by psi is equal to phi n plus phi p upon 2. And so the denominator of this equation number 9a becomes 2 into Ni exponential of QV by twice KT plus 1. And we obtain for V is greater than KT by Q. So we will get this equation for U is nearly equal to 1/2 into sigma VTH into NT into Ni exponential of QV by twice KT. So this is equation number 10. And the reverse current J reverse, which can be written as integration over 0 to W Q into U into dx which is nearly equal to Q into W upon 2 into sigma into VTH into NT into Ni exponential of QV by twice KT. Or this reverse current, which is nearly equal to Ni into NT. So this is next equation number 11. Similar to generation current in reverse bias, the recombination current in forward bias is also proportional to Ni. The total forward current can be approximately the sum of these equation number 10 and 11. So for Pn naught is greater than Np naught and V is equal to Kt by Q, we get the total current. So for Pn naught is greater than Np naught and V is equal to Kt by Q, we get the total current J is equal to Jp plus Jn, which is equal to Js into e raised to Qv by Kt minus 1. So this is next equation number 12, and the total forward current Jf, which is equal to Q into under root dp upon tau p into Ni square upon Nd into exponential of Qv by Kt. Plus Q into W upon 2 into sigma into Vth into Nt into Ni exponential of Qv upon twice Kt. So this is next equation number 13. The experimental results in general can be represented by the empirical form, that is the total forward current Jf, which is nearly equal to exponential of Qv upon Nkt. So this is next equation number 14, where the factor n is equal to 2 when recombination current dominates and n is equal to 1 when diffusion current dominates. When both currents are comparable, then n has the value in between 1 and 2. So with this I conclude this lecture. Thank you.